We like to categorize transfer functions into groups and label them because it helps us understand how a particular system will behave simply by knowing the group that it's part of. We gain some insight into the system if we know, for example, that we're dealing with a type 1 second-order transfer function. And in a similar way, we can glean some additional information about how our system will behave if we know whether it's minimum phase or non-minimum phase. So in this video, we're going to talk about what minimum phase means, what causes a non-minimum phase system, and how that impacts the system behavior. So I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. We can graph the frequency response of a transfer function with a Bode plot. For example, the Bode plot for s plus 2 over s squared plus 3s plus 1 looks like this. The top graph shows how the magnitude of the input signal is altered for each frequency in the spectrum, and the bottom graph shows how the phase is shifted for each frequency. And from this, we can see that if we input a 1 radian per second sine wave into this system, the output signal would have a magnitude around 2.6 decibels lower, and the signal would be shifted by about negative 64 degrees. Or, in other words, the input signal would be delayed by about a sixth of a cycle, and the amplitude would be a little bit lower. But here's something interesting. This isn't the only transfer function that can create this specific magnitude response. We can create any number of transfer functions that produce this, but that all have different phase responses. So the top graph will be the same, but the bottom graph will be different. For example, we could simply add a time delay into our system. If we delay the signal by some amount of time, like the 1 second that I'm doing here, that's not going to impact the size of the signal. It's just going to shift it in time, affecting just the phase. And we can see that this is the case when we graph the frequency response. Notice that the magnitude response is the same, but we've added additional phase. Now, this jaggedness of the phase plot at higher frequencies is just a result of how I'm wrapping the signal when I plot it, so that it stays between plus and minus 180 degrees. And if we input a 1 radian per second sine wave into this function, the phase will be shifted by about negative 122 degrees. So adding additional delay into the system is one way to affect just the phase. The other way is to move one or more of the transfer function zeros from the left half plane over into the right half plane. For this transfer function, we can move the 0 from s equals minus 2 over into the right half plane at s equals plus 2. And check this out. This transfer function also has the same magnitude, but again, not the same phase shift. So we have 3 different transfer functions, and each have the same frequency response magnitude, but different phase. And with this, we can talk about the concept of minimum phase and non-minimum phase systems. The transfer function s plus 2 over s squared plus 3s plus 1 is the minimum phase system for this particular magnitude response. And the other 2 transfer functions are the non-minimum phase systems, which hopefully is obvious from the fact that there is additional phase. Interestingly, even though there is only one minimum phase system for a given magnitude response, there are an infinite number of non-minimum phase systems, which is why you never hear the term maximum phase system. There is no maximum phase shift since we could just delay the signal by any amount of time we want. I suppose a system with infinite time delay, one that just blocks the signal completely, would be a maximum phase system, but clearly that's not useful. Okay, now let's look at the step response for each of these transfer functions and see how the additional phase lag impacts the system in the time domain. The step response for the minimum phase system is the blue line on the far left, and the delayed response is the green line, which predictably just shifts the response to the right by the amount of the delay. The interesting thing here, however, is that the right half plane 0 causes the step response to dip in the wrong direction first, before recovering back to the same steady state value as the other 2. So both non-minimum phase systems produce something that looks like a delayed response. And this makes sense because there is additional phase lag in both of these systems. Okay, so these are the 2 ways that we can create non-minimum phase systems, with a pure transport delay and with right half plane zeros. We have other videos that talk about the transport delay, and I've linked to those videos in the description. So in this video, I just want to focus solely on transfer functions that have a right half plane 0. These systems that exhibit this behavior where the response initially moves in the wrong direction before correcting itself. And to begin, let's look at some systems that exhibit this behavior in real life and see if we can gain a little intuition about what causes it and how it impacts our ability to control it. We encounter systems that initially move in the wrong direction all the time, even if it's so insignificant as to not be noticed. A classic example is pitching an aircraft up to increase its altitude. When the elevator is deflected up, this causes a downward force on the tail, which provides the nose-up pitching torque. And that downward force, however, also pulls the whole aircraft down, slightly lowering the altitude before the airplane has a chance to rotate and increase the lift from the wings. So if you pull back on the control stick, the airplane will drop slightly before heading back up in the direction that you intend. In this case, the dynamics of the system itself has a right half plane 0, and we need to be aware of that when designing a pitch controller for it. And we're going to come back to this idea in just a second. For the aircraft, the dynamics were the cause of the right half plane 0, but sometimes the feedback controller is the one responsible for that 0. Think about the case with a control system that is trying to balance an inverted pendulum on a cart, while at the same time moving the cart to a particular location. To move the cart to the right, the controller first needs to move to the left to get the pendulum angled correctly, and then move to the right. We can see this in action with the inverted pendulum example in MATLAB. And I'm not going to go through the details of this example, but I recommend checking it out if you want to see how to build a controller for this system yourself. But if you just run the default example, it'll show you the result of a tuned control system, and a whole bunch of graphs are going to pop up. Now, the only thing I want to point out for this video is that when the cart is commanded to step some distance to the right, you can see that it in fact does move slightly left first. You can see in the root locus that the open loop transfer function, that's the system dynamics plus the controller, they have a pair of complex conjugate right half plane zeros, and this is what causes the cart to move left before moving right. Actually, for each right half plane 0, the system switches directions. So for 2 zeros like we have here, we'd expect the cart to move right, left, and right again. And if we zoom in on the graph, we can see that this is in fact the case. So that's pretty cool. We can even see this sort of double motion that the cart does using the Mechanics Explorer to animate the inverted pendulum. It does this quick right, left, right dance right at the beginning. Now, I'm not sure this is necessary for the solution. I think you could solve it with a single right half plane 0 and just move the cart left and then right. But at the very least, with this solution, we can see the result of having one or more right half plane zeros. Now, the question you might have is, why does a right half plane 0 cause this strange negative direction behavior? Well, let's take our transfer function from earlier, s plus 2 over s squared plus 3s plus 1, and break it into two parts, the numerator and the denominator. In this way, it's easier to see that the numerator, or the zeros, affect the input into the system, and the denominator, or the poles, affect the response and the stability of the system. So the input is modified in some way by the zeros first, before being affected by the poles. And if we take the inverse Laplace transform of the numerator so that we can see what this is doing in the time domain, we get that the output of this function is the derivative of the input plus 2 times the input. Therefore, we double whatever the input signal is and add to it its derivative to get the modified signal. This modified input signal is then the input into the remaining transfer function. For the left half plane zeros, the derivative and the signal tend to complement each other, since a positive derivative means the signal is moving in the positive direction. So when you add them together, they amplify their positiveness, and this more positive signal can be thought of as the input signal into the second half of the transfer function, which would then respond accordingly. On the other hand, with a right half plane 0, the s is negative. Therefore, the derivative is negative, which counters the direction the input signal is heading in. For example, if the input signal is a step, there's that initial impulse in the wrong direction from the derivative of that step. And this is what's causing that initial wrong direction move. We've modified the input with a wrong direction impulse, which is then fed into the remaining transfer function. Okay, now that we know why negative direction dips occur, we can talk about why it's harder to control systems with these right half plane zeros. First off, if we just think about it, it kind of makes sense that if you have to move in the wrong direction first, then it's going to be a slower response than just moving in the right direction to begin with. And if you tried to increase the speed of the response by increasing the gain of the controller, you could get yourself into trouble. Take the airplane pitch example, and say you've designed a super fast linear controller that could respond to disturbances and errors in the system much faster than the dynamics. You request that the airplane raise its altitude by 100 meters, and you want to do it quickly. The controller deflects the elevator up, which causes a downward force, dropping the altitude a couple of meters. The fast controller recognizes that the error has increased to 102 meters, and so it requests even more elevator, increasing the force more, dropping the plane further, and therefore requesting more elevator, and so on, putting the system into an unstable situation that will eventually max out the elevator range, at which point the airplane will pitch up rapidly and possibly stall, or worse, so clearly not a good situation. We can see that this instability occurs in a more mathematical sense by looking at the phase margin. Let me bring up the Bode plot from earlier with the transfer functions and display the phase margins. You can see that there's about 124 degrees of phase margin for the minimum phase system, and about 86 degrees of phase margin for the two non-minimum phase systems. The fact that they're this close to each other is purely coincidence. As I said earlier, we could have chosen any other delay time, and that would have moved these curves away from each other. The thing to note, though, is that the phase margin is smaller for the non-minimum phase systems because of the additional phase lag. And lower phase margin means that your system is more sensitive to additional phase in the system, and therefore more at risk of becoming unstable. Also, these non-minimum phase systems are more susceptible to increased gain as well. If we increase the gain of the system, that moves this red line up, which increases the crossover frequency. And since phase margin is defined at the gain crossover frequency, we need to follow this down to find that there is more phase lag here, and therefore less phase margin. Or if you prefer to work with a root locus plot instead, we can see the same phenomenon. As a root locus plot shows, as we increase the gain in the feedback loop, the closed loop poles travel from the open loop poles to the open loop zeros. And if one or more open loop zeros are in the right half plane, then as you increase the gain in the system, the closed loop poles will be dragged over to the right half plane as well, creating an unstable system. In the Control System Designer tool in MATLAB, the pink boxes are the locations of the closed loop poles for a given gain. And as I drag them to the right, this is increasing the gain, and eventually the system will go unstable. So just like we reasoned through with the airplane example, increasing the gain in the system, or speeding up the controller, will cause instability for non-minimum phase systems. So what can we do about this? Well, we may be tempted to try to cancel the right half plane zero in the dynamics by placing a right half plane pole directly over it with the controller. This is a bad idea though, because this creates an unstable controller, which could generate some unbounded controller commands, even if the whole system itself appears to be stable. We could also handle non-minimum phase systems with predictive controllers, or other nonlinear approaches. However, the easiest solution is just to slow the system down by lowering the controller gain. If the control system can't react fast enough to error generated by the non-minimum phase components, then it's going to behave as though they weren't there in the first place. For the airplane, if the pitch controller couldn't move the elevator very quickly, then it wouldn't be able to request too much elevator motion before the airplane had a chance to recover from its initial dip in altitude. Of course, this solution produces something that is stable, but at the cost of being more sluggish or having lower performance, but that's a typical result for systems with delay. And delay is a byproduct of non-minimum phase systems. Okay, that's where I'm going to leave this video. I really just wanted to provide a general understanding of what non-minimum phase systems are and how they impact your system's response to inputs. Hopefully, now if you see a linear system that responds initially in the wrong direction, you'll have a better understanding of its cause, and you're going to be in a better position to figure out how to deal with it. If you don't want to miss any future Tech Talk videos, don't forget to subscribe to this channel. Also, if you want to check out my channel, Control System Lectures, I cover more control theory topics there as well. Thanks for watching, and I'll see you next time.